So I'd like to begin the pursuit of a bright, shiny intellectual object called geometric algebra. The motivation for this pursuit is to get Maxwell's equations down to one simple equation, right? We want something equals something, and we want to say that that embodies all of Maxwell's equations. So the only way I know to do this is to construct Maxwell's equations in the context of this new thing called geometric algebra. Now, I'm not an expert in geometric algebra. This is absolutely not a prerequisite to QED, right? You can learn all the QED in the world you want and never touch geometric algebra. But we have been compressing Maxwell's equations, and we might as well compress it to the known end and then come up with an opinion about whether or not geometric algebra is what its proponents claim it to be, which is some universal language that really captures all known essential physical concepts is buried inside this mathematical structure called the geometric algebra. And although, according to the proponents of it, the modern understanding of geometric algebra has never fully blossomed outside of a few fetishists who really, really, really love it. So let's have a look, right? Let's take a little diversion outside of the prerequisites of QED, finish up this idea of how low can we go with Maxwell's equations, and in the meantime, let's learn geometric algebra together. And I say together because I've only done one pass through this subject, and so this is unlike the other topics here that I've gone through in this channel that I'm extremely familiar. I'm actually going to be learning this one about the same rate that you will if you follow along. I've done a full pass on the subject, so I am ready to begin. So this will be my second pass through the subject. But I do find it very interesting, and I'd like to get your opinions on it. So with that being said, let's begin. So the way I propose to study this material is I'm going to pick one particular paper. This paper is called Space-Time Algebra as a Powerful Tool for Electromagnetism by Justin Dressel, Konstantin Y. Blioch, and Franco Nori. And they're at nice good institutions, right? Electrical and Computer Engineering at California Riverside, Emergent Matter Science, that's really interesting, in Saitama, Japan, Interdisciplinary Theoretical Science Research Group, Wakoshi Satima, Japan, and Ann Arbor, Michigan, the University of Michigan. So we have a nice mix of very qualified people, I'm sure. I don't know any of them. But I've gone through a lot of papers about the subject of geometric algebra, and they're all good in their own way. This one I feel is the best. I'm very, very excited to review this paper again, and that is the plan. We are going to read this paper together, or the good parts of the paper together, or I shouldn't say, it's all good. I guess I should say the dense parts together. And it's very ambitious, right? Because the paper wants to introduce space-time algebra, which is just one form of geometric algebra, right? So the concept of geometric algebra is actually quite broad. It covers many different possible algebras. But space-time algebra is only one, and it's the one that is applicable to special relativity. And it's the one that's applicable to understanding the vast majority of space-time physics in flat space-time. And so this paper has to teach geometric algebra, specialize it to space-time algebra, and then apply it to the study of electromagnetism. So it's trying to do an awful lot. And as such, it refers to other papers about the algebra itself, and we're going to make those hyperlinks together. I'm going to try to fill in the gaps that are necessarily present for such an ambitious paper. So if we look through the contents of the paper, they talk about the motivation, and we should go through that a little bit. And then they talk about the insights. This is the fetishist part, meaning that anybody who's really excited about geometric algebra really likes to talk about why it's so good and all of the special insights you gain by using this approach as opposed to any other approach. And so I think actually we'll probably skip this, right? And what we'll do is we'll proceed directly to the approach, which is section 3 of this paper, and we'll let you decide how the insights surface. And then in the end, maybe we'll go back and have a look at the insights. Or perhaps as we go through this, when we discover insights that are cited up here, I'll make note of it. But I think it's better just to dive right into it and let the insights sort of percolate by themselves. All right? The second section, a brief history of electromagnetic formalisms, we probably will not discuss that. This goes through some of the battles between the quaternion formalism versus the Gibbs Heaviside vector formalism versus the formalism of differential forms and a few other formalisms that are in there. Suffice it to say, all of these formalisms in the history of the study of magnetism are derivable, buried in, a subpiece of, or somehow contained within the space-time algebra, which is one of the important motivations, right? All of these formalisms from the day that Maxwell started the mathematical construction of the theory of electromagnetism all the way to the present day, all those formalisms, it turns out, can be unified in one form. And that's the claim. That's the big claim, and that's why we're studying it. So the space-time algebra, so when you see space-time algebra in this paper, that is the geometric algebra of space-time. And I'll have to spend a little time teasing apart the distinction between the special instance of geometric algebra, which is space-time algebra, from the body of all geometric algebra. So I'll take care of that. And then they talk about the basic components of the algebra, which are the multivectors. Then they go through a whole bunch of ways of understanding how multivectors work in the space-time algebra. We're going to immediately cover this section. I've actually brought these pieces, this section of the paper, which I guess is 16 to 44, I've actually put them right here into our lesson plan. And in order to finally get Maxwell's equations, we're going to have to do the space-time calculus and Maxwell's equations in a vacuum. And then notice they also do a lot of other stuff. I don't know if we'll go all the way through everything here. What I'd like to see us get through section 5. So we'll begin with section 3. We'll shoot for section 5. I don't know how long this will take. I don't know how quickly it will go, but it will certainly be very, very interesting. All right, so let's begin. Oh, and by the way, if you want this paper, here you go. This is where you'll find it. You'll find it in the Cornell Archive database, Space-Time Algebra as a Powerful Tool for Electromagnetism. And this is the identifier right here, Archive 1411.502. So anybody can get this paper and read along with us. All right, so let's begin. Here's section 3, and let's begin with this quote by David Hestenes. I don't know exactly how to pronounce his name. I should check. Hold on. Okay, so I found a lecture by him, and he pronounces it David Hestenes. He pronounced it David Hestenes. And let's have a quick look at what he says. Mathematics is taken for granted in the physics curriculum, a body of immutable truths to be assimilated and applied. The profound influence of mathematics on our conceptions of the physical world is never analyzed. The possibility that mathematical tools used today were invented to solve problems in the past and might not be well suited for current problems is never considered. Okay, so that's his position. Now, first of all, Mr. Hestenes is very acclaimed. This guy he's no fly-by-night. He's a real physicist. He's been thinking about this literally his entire career. And he's unambiguously a very brilliant man. And he's an evangelist for geometric algebra. And interestingly, I've arrived at a pretty advanced state of my knowledge of physics, and I never heard of it. I never heard of geometric algebra until stumbling through this material. So unfortunately, despite this evangelism, I'm not sure that he's made a lot of real progress penetrating to regular students of the subject. So, of course, that really depends on where you stand, but where I stand, it's a very new idea. Now, what he's suggesting, of course, is that, hey, all of the mathematics we're using today, this is the part right here, the mathematics we're using today is not adequate for the work we're trying to do. And he says it's never considered. I tend to doubt that. I've met a lot of theoretical physicists who are always chomping at the bit for some kind of new mathematics. I think immediately about supersymmetry, which is a radically new form of mathematics interjected into the subject of Lie algebras that really people jumped on. Understanding that the current conception of Lie algebras is insufficient for the study of certainly of the study of supersymmetry. On the other hand, it's definitely the case that, so I'm not completely sure that the idea is never considered is all correct. On the other hand, the basic point that he's trying to make here, or that the paper's trying to set up here, is that it's time for us to understand that the way we formulate at least electromagnetism is not adequate for what electromagnetism is. And that's sort of the excitement that those who are interested in this subject are trying to get us all, us lay scientists, to understand. Is like, hey guys, look at this. This is the way we need to approach and think about this. So let's give them their day in court and let's read through this paper. Physically speaking, space-time algebra is a complete and natural algebraic language for compactly describing physical quantities that satisfy the postulates of special relativity. So right away, that first sentence is very optimistic. It's very exciting, right? We have a mathematical structure that compactly describes special relativity. Now, we've already had one that describes Newtonian relativity, right? Or Newtonian, or I guess Galilean relativity. But bonding everything together into something that naturally describes special relativity is definitely exciting. Mathematically speaking, space-time algebra is the largest associative algebra that can be constructed with the vector space of space-time equipped with the Minkowski metric. All right, so this is the first place we are going to stop and make sure that we fully understand what's going on right here. We're looking for, we've got the notion of an associative algebra, the vector space of space-time equipped with the Minkowski metric. So let's go ahead and let's break this down a little bit. All right, so we'll begin with the idea of an algebraic structure. And now an algebraic structure is also called an algebra, right? An algebra. And so these are sort of synonymous, right? It has to do with a particular mathematical structure that exists in the subject of abstract algebra. And let's quickly review what an algebraic structure has to contain. What is it? How do we create an algebraic structure? And we begin with a vector space, right? And you remember, I always sort of draw vector spaces with a little box. I give it a name, V, for vector space. I define a basis in the vector space usually, and I'll write the basis as E mu, right? Those are the basis vectors of a vector space. The vector space has an addition defined on it, and it has, very importantly, some bin of scalars, right? This is a bin of scalars, and that bin of scalars comes from some field F, right? So the field F could be the real numbers or the complex numbers traditionally, right? Traditionally, it's either real or complex numbers, but it could actually be any field. We, for the purpose of our work in this material, we're going to do real numbers because we're dealing with special relativity, and special relativities deals with the real number manifolds on space-time, or vector spaces with real scalars. So our scalar field is going to be the real numbers. It's quantum mechanics that uses the complex numbers for scalars. So our vector space, here it is, right? And now what makes it an algebra, though? A vector space is not an algebra, right? This is just a vector space. So to make it an algebra, we have to add a bilinear operator. And a bilinear operator is often called a bilinear product, right? And it's often referred to as just multiplication. And the idea is any two vectors in the vector space, right? If we pull out one vector v, we pulled out, say, vector v, and then we pulled out a vector w, right? We can certainly add v, w plus v using the basic addition of vectors, right? That's this addition. It allows us to add any two vectors. We can certainly multiply by a scalar, right? If we pulled out a scalar little b, we can certainly write bw, right? Bw is the scalar b multiplied by the vector w to give us a new vector, which we call the vector bw. Now notice this is a multiplication, right? This is a multiplication just like the new one that we're going to create. We have to create a multiplication, a bilinear operator, a bilinear product. We have to create one, but we already have one. We have what's called scalar multiplication, right? Scalar multiplication, right? That's what this is. We've got a scalar here and a vector here. I guess I should make my vector red, right? So scalar multiplication already exists. And scalar multiplication is linear, so we know that b times w plus v equals, forget the colors, it's bw plus bv, right? As long as we know that b is the scalar and w is the vector. Maybe I'll do this for now, right? I'll put little vector symbols over that to make sure we have a distinction between our vectors and our scalars. I guess there's one there too. So we already have that, and this is what makes it linear, right? This is what makes it linear. So we are now seeking a new multiplication, and this is a multiplication that works for vectors. It's the vector w multiplied by the vector v, and we can put them right next to each other just like that. And this needs to return another vector, which I guess I'll call y, right? So this is now a multiplication, a bilinear product of, or bilinear operator. I guess there's no operator here. If I wanted to do an operator, I would have to maybe do something like w star, we'll put a little star for the v, and now star, this guy here becomes the so-called operator that we're seeking, right? But if I just put it next to each other like this, the operator is implied, right? There's sort of an implied star right here between the W and the V. So, so now I need to create this new operation that takes two vectors and produces another vector, right? And by vector, remember, what we just mean is an element of this vector space, right? We're not talking about yet. We're not talking about little pointy things that go off in a direction. And when I used to teach this, or when I taught this in the what is a tensor section, I really emphasized that this thing, I didn't even want you to call it a vector. I wanted you to call it a little pointy thing so you would erase this from your thinking. When you think of a vector in this context, you're only thinking of it as an element of this vector space, which obeys some rules, right? This addition rule, it's got a basis. The basis, by the way, has to have some dimension assigned to it, so I should actually include that in my list of things here. We have to assert some sort of dimensionality of the vector space. The vector space is quite abstract, right? But it will have, as long as it's finite dimensionality, it'll have a you have to assign it a finite dimension, presuming that you want a finite dimensional vector space. We can talk about infinite dimensional vector spaces, but we're not for any of the work we're doing here. We're always going to talk about finite dimensional vector spaces. In fact, we can even go one step further and just go ahead and say n equals 4. We're dealing with a 4-dimensional vector space, and we're dealing with the unit vectors E0, E1, E2, and E3. Right? That's what these E mu's are, just those 4, starting at 0 and going to 3. We might as well, because that's all we're going to use in this collection of material. But the point is that once we have a vector space, in order to promote it to an algebra, we have to create this bilinear product. And in this case, bilinear means something very straightforward. This new multiplication we're inventing is linear or bilinear with respect to the addition operator. So you get v multiplied by, or w multiplied by vector v plus vector s is vector w multiplied by vector v plus vector w multiplied by vector s. And notice that this is the addition operation for the vector space, which means that this here, right, this guy must be an element of the vector space v, and this guy must be an element of the vector space v, so we can actually add them together. Otherwise, addition doesn't make sense, because addition is only defined between two vectors in the vector space. So that is what an algebra is, but you'll also notice that it used the word associative algebra in the sentence that we're deconstructing, and that's pretty simple. That just simply means w v. Now I'm omitting the operator symbol. Whenever you see two vectors next to each other like this, there's only one multiplication operation between them, so there's no ambiguity, so we can just sort of drop it, right? We could actually erase it here, we could erase it here, and erase it here, and we'd still be fine. So, but the point is WVS, we can multiply those two first, and that would be the same as WVS if we multiplied those two together. Some of the most important algebras in physics, in particular the Lie algebra, are non-associative, right? We're not going to worry about that now, but just understand that for what we're doing, we have an associative algebra, and so that is what geometric algebra is. We're going to somehow create vector spaces. We're going to define this multiplication on this vector space, and somehow we're going to create a vector space that's four-dimensional, and somehow this is going to completely reassemble our understanding of space, time, and the subject of electromagnetism. So let's go back here. What have we done? We figured out this word, associative algebra, that can be constructed with the vector space of space-time equipped with the Minkowski metric. So obviously, they're going to use what they're calling the vector space of space-time and the Minkowski metric on that vector space to create this associative algebra. So I guess we need to understand, what do they mean by the vector space of space-time? What is this all about? And equipped with the Minkowski metric, what is that all about? Those two are much easier, because what I suspect that they're doing here is, because space-time is flat, this vector space is going to be space-time itself, positions in space-time. So a space-time coordinate of t, x, y, z, right, a space-time coordinate like that, is going to be transferred into a vector that's going to be TE0 plus XE1 plus YE2 plus ZE3, right? And we're going to, because space-time is flat, you can do this. You can treat the points in space as though they are vectors, and by doing so, you sort of vectorize space-time, right? And then the last thing is pretty obvious. They're just saying that we're going to use the Minkowski metric, where eta, alpha, beta is this diagonal. It's either one of these two diagonals. I can't quite remember which one this paper used. We'll find out in a moment, I'm sure. And that allows us to find the distances between two events in spacetime. So if I express an event in spacetime in this form, its distance to another event in spacetime is a contraction of this vector against this metric, the Minkowski metric. So that's all that means. And we'll see exactly how they push that in there pretty soon. All right, so let's go on. The spacetime algebra is an orthogonal Clifford algebra, which is a powerful tool that enables manifestly frame-independent and coordinate-free manipulations of geometrically significant objects. Okay, wow. So here I'm interested in this word, I'm interested in this question of geometrically significant and frame-independent and coordinate-free manipulations. So, okay, so first of all, this notion of it being an orthogonal Clifford algebra, well, that's what the spacetime algebra is. So that's just really, we can treat that right now as just another word for the spacetime algebra. Manifestly frame-independent. Well, my understanding of frame-independent has always been that you don't bust things out into coordinates right away, which is another way of saying we don't select a basis. We don't select a specific basis necessarily right away. That's what coordinate-free is when we create our vector space, we have one special chosen basis. And I think as we go through this, we're going to actually see that we're going to do a lot of proofs using coordinate bases because it's a lot easier in some cases. However, you don't have to do that. I'll try to show a few examples as we go on. But the idea is that one of the problems with studying special relativity is you have to say, oh, you know, we've got the lab and we've got the moving guy, and here's what it looks like from the lab, and here's what it looks like from the moving guy, and you have these coordinate transformations. Presumably, we can kind of get away from that by putting everything in the context of the space-time algebra. We escape this need to refer everything to some coordinate system. So we'll see how that claim pans out. And what is the notion of a geometrically significant object? Well, so to me, a geometrically significant object is anything that can be described as a field over the space-time manifold, right? That to me is what geometrically significant means. So we'll have to see exactly what they mean, but vectors certainly are geometrically significant objects. Forms are certainly geometrically significant objects. But notice object is now, this is a mathematical construction we're talking about. We're talking about a mathematical object that models something about physical reality. So presumably we have physical reality and a bunch of mathematical objects that can be placed on a manifold. Our physical reality exists in some sort of manifold of space-time, right? A four-dimensional manifold of space-time in special relativity. Anything that can exist inside this thing as expressed in the terms of a vector or tensor field, that is a geometrically significant object from my understanding. Okay, so moving on. Unlike the dot and cross products used in standard vector analysis, the Clifford product between vectors is often invertible and not constrained to 3 dimensions. Okay, so right away they've introduced this notion of Clifford product, right? So that Clifford product, I see it's actually on 2 parts, Clifford product, right? So that's our bilinear multiplication of vectors, right? They're giving it the name the Clifford product. So make no mistake, when we build our space-time algebra, the product between the elements of the vector space we're dealing with is the Clifford product. They call it the Clifford product. So we'll use that word from now on. That is, whenever I describe this bilinear operator, right? This bilinear operator and this multiplication that does all of this stuff, we're now going to call that the Clifford product, the glorious Clifford product, all right? That's what that is. So what about it? Well, the Clifford product between vectors is often invertible. Oh, that's interesting. Yeah, so, okay, I didn't realize they made such a deal out of that, but it's often invertible and not constrained to 3 dimensions. This one I'm real familiar with, right? They want to make a big point here is that the algebra that we're constructing for space-time, you can construct an algebra for any dimensionality out there. And it's not the space-time algebra at that point. It's a different form of the geometric algebra. But it immediately generalizes to any number of dimensions. And this is not true of the mathematics we have learned for electromagnetism, right? This notion in particular of the cross product. The cross product cannot be defined except in 3 dimensions. And but the cross product is, right, there is a vector cross another vector, and it does equal another vector, right? So the cross product looks a lot like an algebra. And indeed, in 3 dimensions, the cross product can be understood as the bilinear operation that defines an algebra. But as soon as you go to 4 dimensions, this cross product idea breaks down. It only works in 3 dimensions. I think it also works in 7 dimensions or something. I've never really explored that, but you can somehow, for some reason, you can define a cross product in 7 dimensions of all things. But you certainly can't do it in 4, 5, 6, 8, 9, or other dimensionalities. So immediately, having the idea that our electromagnetism can be forced into a mathematical structure that has great generality otherwise, that actually is compelling, right? That's interesting. It's like, okay, our universe has settled in on one particular mathematical structural form of many. And you can speculate why that might be. So that's interesting. The notion that it is invertible, see, the idea that this is invertible, let's see, where did it say? Right here. That's interesting, right? That basically that's saying that if I have a vector W, there is a vector Z out there such that W times Z is essentially the, it's some kind of unity, right? Now, there is a problem here, right? There's no such thing really as a unit. There are ideas of unit vectors, but there's no such thing as a one in the world of spatial vectors, right? So this notion here is actually quite important and interesting, because what I want to write down is that the Clifford product between W and Z equals 1, ergo Z is the inverse of W and W is the inverse of Z. But 1 is not a vector. 1 is a scalar, right? 1 is a scalar. And so this notion of inversion is already strange if you think of these vectors as little pointy things. So we're going to understand what this idea of invertible means as we go along. But it is a very important point to take note of, is that the idea of being invertible for 2 vectors being multiplied together to give you a third vector, that is actually a puzzle. It turns out it's solved by broadening our notion of what a vector is, right? Remember, a vector is an element of a vector space. So basically, a little foreshadowing here, if I add the scalars directly to the vector space, right? So the vector space contains like a bunch of little pointy things and all the scalars. Well, now 1 is part of the vector space. And in principle, this Clifford product between 2 little pointy things might actually be a scalar, because the scalar is now inside the vector space. Now these 2 little arrows up here, they don't mean I'm a part of the vector space. They mean I'm a part of the vector space, but I'm a little pointy thing also, right? And you might have to put some other symbol up here, or the absence of a symbol says, oh, I'm a part of the vector space, but I'm a scalar. So we'll see how that works as we move on in the early phases of discovering how this is all put together. And then we read, unlike the component manipulations used in tensor analysis, which we've done already, space-time algebra permits the compact, component-free derivations that make the intrinsic geometric significance of physical quantities transparent. So I guess the physical quantity that I'd like to see the geometric significance of is the electromagnetic field tensor F, right? That's a tensor, right? So perhaps there is something in geometric algebra that takes that tensor from being this very abstract mathematical idea and lifts it into something that's obvious. Likewise, a differential form, right? Omega, right? That is a, we treat fields as a physical quantity described by, say, a two form, right? And the two form omega, we already have some notion of how omega is physically significant. Maybe this brings it out even more. All right, let's continue reading. When space-time algebra is augmented with calculus, then it subsumes many disparate mathematical techniques into a single comprehensive formalism, including multilinear algebra, vector analysis, complex analysis, quaternion analysis, tensor analysis, spinor analysis, group theory, and differential form. So this is it. This is the evangelism here, right? All of those things that you have to learn, you could take a class in each of those subjects. Well, somehow geometric algebra takes all those things and puts them in one comprehensive mathematical framework. That's actually pretty exciting, right? So that's part of our motivation, right? Actually, earlier I said, oh, you know what? We're not going to spend a lot of time on this motivation, but apparently they slipped in some of the motivation right here. So we're having to deal with some of the motivation. All right. Moreover, for those who are unfamiliar with any of these mathematical techniques, space-time algebra provides an encompassing framework that encourages seamless transitions from familiar techniques to unfamiliar ones as the need arises. As such, space-time algebra is also a useful tool for pedagogy. So that's pretty hopeful, right? The idea that you would take this thing, which is still kind of obscure, this idea of geometric algebra, and all of a sudden it's going to be used to teach people stuff. You really want to move it to the mainstream. So the people interested in this subject really feel like this is ready for prime time. And the final paragraph that we'll read today is, during our overview, we will make an effort to illustrate how space-time algebra contains and generalizes all the standard techniques for working with electromagnetism. Hence, one can appreciate space-time algebra not as an obscure mathematical curiosity, but rather as a principled, practical, and powerful extension to the traditional methods of analysis. As such, all prior experience with electromagnetism is applicable to space-time algebra approach, making the extension readily accessible and primed for immediate use. Okay, so there you go. This is why we're doing what we're doing. So the next time we will begin by studying exactly how they define and create space-time, and how we'll actually construct the space-time product. So we'll get through section 3.1, and hopefully we'll get well underway into section 3.2. All right, see you next time.